Bill Gates and pandemic preparedness. In 2010, he called the years ahead the decade of vaccines. He urged the world to build systems to stop epidemics. By 2015, he was warning that the world was not ready for a fast-moving virus. That sequence looks like careful foresight. It also looks like an investment timeline. The Gates Foundation backed vaccine research for years. It helped fund global programs that turned basic lab work into scaled production. In 2022, the foundation committed up to $125 million to end the acute phase of the recent pandemic and to prepare for the next one. In January of the same year, the foundation and Wellcome each pledged $150 million to a pandemic preparedness coalition. Those sums strengthened vaccine manufacturers and distribution systems around the world. When the global outbreak arrived in 2020, people noticed how many pieces were already in place: funding networks, manufacturing capacity, distribution plans. Gates had been advising on these gaps for a decade. He had also pushed for mRNA technology and manufacturing in parts of the world that later struggled without enough vaccine supply. None of this proves secret planning. Public health experts had long said the world needed these systems. Still, the pattern is striking. Years of warnings, then years of funding, then a pandemic that made those systems essential. What are the odds that this combination of warnings and investments would line up with a crisis that made them central to the global response? He had also pushed for manufacturing capacity in regions that had little vaccine production. That effort meant paying for technology transfers and training. It meant money flowing to factories and to the people who run them. Those moves were not small. They quietly shifted where vaccines could be made when global demand exploded. One visible result was the role of major manufacturers in low-income countries. With support, they ramped up production. In 2021, 1.5 billion doses came from a single large producer. That volume mattered. It changed how supply chains moved and who could deliver vaccines to vulnerable places. Some critics point out another uncomfortable detail. Private foundations often work with companies. When those companies succeed, they make money. The foundation model separates charitable grants from for-profit returns. Still, the public sees a loop: advice, funding, later opportunity. That sequence fuels suspicion, even when each step has a public health rationale. At the same time, the foundation backed global mechanisms that aimed to make distribution fair. The COVAX effort sought to get doses to countries that otherwise would be last in line. Funding from private and public sources helped deliver billions of vaccine doses across the world. Those successes are real. They saved lives, so what do we make of it all? Is this pattern the result of long-term public health planning paying off at the exact moment it was needed? Or is it a strange alignment of foresight, influence, and timing that looks a lot like coincidence? The question cuts both ways. Mark Pincus and UFO research. In 2021, a private proposal landed on his desk. A contractor said they could recreate military exercises that had been visited by strange craft. The contractor asked for $1.5 million to run experiments and to document disruptions to radios and electronics. They described objects that moved in ways pilots could not explain. Conversations started and then stopped. Emails and meetings that once showed momentum went quiet. The project did not move forward. That silence alone is unusual in venture worlds where follow-up happens fast. It is more unusual when the subject is an alleged physical phenomenon that interferes with military gear. Months later, he attended a small event where witnesses had gathered. He took photographs of a large drone-like object at night. The images show a shape that some described as unusually stable and without obvious propulsion. He has been careful not to claim contact or to make bold statements. He frames it as curiosity about possible physics breakthroughs rather than as proof of anything. Meanwhile, official bodies stepped up. In 2020, the Department of Defense created a task force to track unexplained aerial events. In 2022, a broader office formed to coordinate investigations across domains. Those efforts are public and ongoing. Scientists warn that most reports have mundane explanations. But they also say some encounters remain unexplained. Here is the uncanny part. A pitch appeared seeking private money to study odd signals near military exercises. The pitch faded. Then a private sighting followed. And at the same time, government units were formalizing their investigations. Coincidence is possible. The pattern also looks like a small private doorway opening briefly into a larger public mystery. Some experts push back. They note that most unexplained sightings end up having ordinary causes. Sensor errors, misidentified aircraft, atmospheric quirks, and sometimes honest mistakes explain a majority of cases. Scientists who study these reports say that a few remain unexplained after careful review. Unexplained does not mean impossible or supernatural. It means the current data do not fit known explanations. That uncertainty matters here. A private pitch asked to recreate conditions where interference occurred. That implies a testable claim. Replication is the core of science. The sudden silence around the pitch left no replication and no data for public scrutiny. Without data, a private sighting is only another report. There are also public policy questions. When private money enters an area that could overlap with national security, who gets access to findings? Government task forces now collect reports and aim to coordinate analysis. Private projects may share with officials. They may also keep results private for proprietary or safety reasons. That mix of secrecy and disclosure creates an awkward public image. Another angle is technology. If some encounters reveal novel effects that disrupt electronics, that would interest physicists and engineers. Private curiosity could accelerate study, or it could produce private claims without peer review. That trade-off sits at the heart of this story. So where does that leave us? A contractor pitched a study for $1.5 million. The pitch died. A private witness photographed an odd craft. At the same time, the government formalized investigations into these phenomena. Does that sequence add up to meaningful coincidence? Or to a set of loosely connected events that only look strange when placed side by side? Think about it and tell someone who follows modern mysteries. Paul Allen and SETI. In 2007, a radio telescope array went online at Hat Creek. It began with 42 6-meter antennas aimed at listening for signals that might come from other minds. The array was not just another instrument. It was built to run continuous surveys and to test ideas about technosignatures that few public programs could fund. The initial years were promising, and then they were rocky. A funding shortfall forced operations to pause in spring through winter of 2011. That gap showed how fragile privately started science can be. The array survived because partners and new donors stepped in and because the instrument itself could be upgraded. Between 2013 and 2016, the receivers were improved. Engineers added cryogenic feeds that cooled the sensors and cut background noise dramatically. That change meant the array could hear fainter whispers from deep space. Around 2019, a private initiative funded a new digital backend that sped up how fast the array could sweep the radio spectrum by roughly 10 times. Faster searching makes it more likely to catch short-lived events. That technical story matters because it is simple. Better receivers and faster processing change what you can discover. A piece of hardware paid for by private money moved the needle on sensitivity and on search speed. The result was a telescope that returned to steady science and began to contribute to searches that public programs alone had struggled to sustain. What happens when a privately funded instrument hears something ordinary or something odd? Who owns the data, and who decides what to publish? Those questions follow naturally from a project that began with one donor and grew into a facility used by many. The upgrades paid off in ways that mattered. In recent years, the array caught bursts that repeat. Scientists recorded 35 bursts from one repeating source over 541 hours of listening. Those detections show the instrument can follow fast radio bursts in real time and help point other telescopes to the same patch of sky. It also ran the longest single target search of TRAPPIST one ever attempted. For 28 hours, the array scanned a narrow band looking for technosignatures that would stand out from natural noise. No artificial signal was found. That negative result is still useful. It narrows where to look next, and it trains the software to ignore false alarms. Then, the array helped on a different kind of discovery. It provided radio data for a tidal disruption event that revealed a hidden black hole tearing a star apart. That finding shows the facility is not only for hypothetical searches, but also for real-time astrophysics that changes how we map the universe. Ownership and access became practical questions. Who gets to analyze raw files when private donors fund the hardware? Who decides to release a candidate signal? In science, the answer is usually peer review and open data. In practice, private funding creates extra steps before the public can see the full record. There is also a simple truth about capability. Cooling sensors and improving digital processing changes what you can hear. A quieter feed and 10 times faster spectrum scanning make new discoveries possible. Private money moved the needle on sensitivity and on speed. So, think about this. A privately funded array went from startup fragility to contributing to frontier science. It detected repeating bursts. It ran the deepest single-target technosignature search. It caught data on transient cosmic events. If a privately funded instrument hears something truly unexplained, who gets to verify it, and who gets the credit? Eli Broad and genetic research. An initial 100 million gift arrived in the early 2000s. A second 100 million followed soon after. Then, a 400 million endowment turned the effort into a permanent center. Those gifts did more than name a building. They created capacity few universities could add on their own. The center hired big teams. It built shared facilities and brought clinicians and computational experts under one roof. With that foundation, the Institute secured major competitive grants that amplified the original gifts. A 15 million grant helped map epigenomes. A 40 million award funded whole genome sequencing for 20,000 people to search for genetic causes of disease. A separate 32.5 million initiative created a new observatory for mapping cell circuitry. Those projects moved fast because infrastructure and staff were already in place. Results followed. Teams identified genes linked to heart and lung conditions. They built maps that explained how cells decide which genes to turn on or off. They created tools that other labs use. The work accelerated drug target discovery and pushed genomic medicine into clinical studies sooner than many expected. This is the crucial pattern. Large private donations created durable capacity. That capacity attracted public funding and large projects. In practice, the initial private choice shaped which scientific questions rose to the top. That influence is not secret. It is visible in who was hired and what projects launched. The question becomes practical. When private philanthropy builds the scaffolding for major biomedical breakthroughs, who sets the agenda and how transparent are those choices? Chapter 4, second half. Complete the Eli Broad chapter, with implications on influence access, ethics, and shareability, finishing with a rehooking question. Maintain voiceover rules and no repeat of the chapter header. The gifts built labs and hired talent. They also created influence over research priorities. When a center controls sequencing machines and data pipelines, it steers which diseases get deep study and which get less attention. That steering can save lives. It can also shape which companies get spun out and which therapies reach clinics sooner. There are practical tensions that follow. Private donors sometimes fund programs that later partner with pharmaceutical companies. Those partnerships can speed drug development. They can also create complicated ownership of discoveries. Patents and licensing deal with who benefits when a new target becomes a successful therapy. Transparency becomes the currency everyone asks for. Another issue is access to data. Open science is the standard ideal. Many journals and funders expect data to be shared. In practice, some datasets stay behind institutional gates for a time. That delay can slow replication and independent review. It also creates a perception problem. When private money pays for critical resources, the public wonders who sees the raw material first. There are defense and privacy angles too. Human genomics touches on consent and on sensitive health information. The Institute set up frameworks to protect participants. It still faces questions about who controls recontact, who can use the data for commercial research, and how to balance discovery with individual rights. Despite these questions, the scientific returns are real. Better maps of cell control led to new ways to think about disease. Whole genome projects revealed surprising links that guide clinical trials. The initial gifts changed timelines. They made big projects possible years earlier than would otherwise have happened. So the core tension is simple. Private philanthropy can accelerate breakthroughs and save lives. It can also concentrate power over which questions get answered and who profits. Which matters more to you, the speed of discovery or the checks that keep science open and fair? Jeff Bezos and Blue Origin. He started Blue Origin with a simple line of thinking. If launch costs drop, then more people and more projects can go to space. That idea turned into rockets and test stands, and a private ecosystem focused on reuse and long-term access to orbit. New Shepard became the face of that effort. It was built for short suborbital hops and for space tourism. The vehicle flew unmanned tests and then carried private passengers. Those early tourist flights proved a concept people had only read about in books. The capsule design emphasized passenger experience with large windows and cushioned seats. Safety testing was relentless and public. Behind the scenes, Blue Origin also built a heavy-lift rocket called New Glenn. That vehicle was designed to reuse a first stage and to carry larger payloads to orbit. New Glenn is meant to compete in the same market that changed the economics of launch. The company also joined with partners on Orbital Reef, a commercial station idea meant to host research and industry in low Earth orbit. That plan imagines a mixed-use business park in space. There is a pattern worth noting. A private billionaire invested billions of his own money into hardware that changes who can fly and what can be launched. That funding created commercial ferrying, tools for research in orbit, and a push toward lunar experiments. Blue Origin also moved into lunar support work by building robotic components that partner missions can use. Some call this visionary. Others call it strategic timing. Either way, the coincidence is clear. Private cash flowed into launch and infrastructure well before a broader market formed. That timing means when demand rose, there was private capability ready to meet it. The payoff was new flight opportunities, commercial station plans, and a seat at the table for lunar missions. Who benefits most from that readiness remains a conversation that continues beyond the launch pad. That readiness created practical advantages. When governments and companies began buying launch services, there was capacity from a private firm already tested and crewed. Blue Origin could bid on contracts and offer station services because it had spent years building rockets and testing capsules. That is the payoff of early heavy investment. Competition mattered too. Rival firms pushed costs down and spurred innovation. At the same time, procurement processes and regulatory choices shaped who got early contracts. Private programs that already had hardware found it easier to win work, or at least to be invited into partnerships. Partnering with other companies on a commercial station or on lunar robotics shows how private funding becomes public-facing capability. There are criticisms worth noting. Some argue that public money and policy should favor fair competition and broad access rather than concentrated readiness. Others point out that private investment reduces taxpayer burden for risky development. Both points have merit. The result is a mixed landscape where private readiness meets public need, and both sides negotiate access and rules. Safety and reputation are part of the story. Early test failures and high-profile flights attract scrutiny, but they also prove concepts. When a company demonstrates safe, reusable stages and crewed capsules, it changes regulators' minds and opens new markets for science and tourism. Finally, there is the social question. Who benefits from being first to fly and first to offer orbital real estate? Is it a public good when private fleets expand humanity's reach, or a private windfall for a few? The timing makes the question urgent, because the capacity was built well before demand exploded. Decide for yourself and tell someone who follows space news, Elon Musk and SpaceX. He bet his own money, and then pushed the company to try things most thought too risky. The core idea was simple. Reuse the first stage, and the cost of reaching orbit drops fast. Falcon 9 and Falcon Heavy proved the concept. Engineers learned to land boosters and fly them again. Over 200 successful reuses showed it works. That technical leap matters in plain terms. If each launch costs a fraction of earlier prices, more missions become viable. Satellite companies can afford frequent replacements. Science teams can send larger payloads. National programs can buy more launches for less money. In a short time, a private firm moved launch economics into a different bracket. SpaceX did not stop at reusability. Starship is built to carry enormous payloads to orbit and beyond. The vehicle aims to move 100 to 150 tons at a time, and to stage missions that go to the moon and to Mars. The plan set timelines for uncrewed test flights and for crewed missions in the coming years. Those ambitions reshaped conversations about Mars colonization from science fiction to roadmaps. There is a market consequence. When a private company cuts costs and proves hardware, it attracts customers and contracts. That readiness helped it win work and to be invited into public partnerships. It also forced competitors and regulators to adapt faster than they might have. So the pattern looks clear. A billionaire backed bold engineering that lowered barriers well before demand peaked. The coincidence is that capacity existed just as a broader market, and public programs needed it. Do you see that as visionary timing or as concentrated advantage? Tell someone who follows space. The practical results have been striking. Lower launch costs made missions that once seemed unaffordable suddenly possible. New classes of satellites went up. Science payloads that needed frequent replacement became realistic. Governments found more options when buying launches or planning experiments. That advantage translated into contracts and partnerships. Firms that had flying hardware were invited into big projects and into public-private collaborations. Regulators faced new realities. They had to adapt safety rules and licensing to reusable stages and rapid flight rates. That process moved faster because a private provider had proven the hardware in public tests. Safety and environmental concerns followed. Reusability requires many more launches and recoveries. That increases community scrutiny near launch sites. It raises questions about noise, air quality, and local impacts. Companies show data and tests to reassure officials, but public confidence requires transparent reporting and strong oversight. There is an economic angle. Faster, cheaper access to orbit stimulates new business models and new jobs. It also concentrates industrial capacity. When a single firm develops a dominant launch capability, it can influence supply chains and talent flows. Competitors respond by innovating or by seeking different market niches. Finally, there is an ethical and strategic question. If one private actor builds readiness years before demand peaks, is that visionary stewardship or a concentration of advantage that limits fair competition? The timing is uncanny. The infrastructure existed just as public programs and commercial markets expanded. decide what you think. Is rapid private innovation the engine that benefits everyone, or the source of power that needs stronger public rules? Tell someone who follows space, and leave your answer in the comments. Mark Zuckerberg and Chan Zuckerberg Initiative. They began with an ambitious pledge to give away 99% of their shares and to fund education and community projects. Over time, the focus shifted. In 2025, the organization announced a major reorientation toward AI-powered biology. That change included buying an AI research lab to speed experimental work and to build virtual cell models. At the same time, they moved away from some education programs. A flagship school that provided free services was slated to close after years of operation. Social advocacy and DEI grants were reduced. Those cuts surprised groups that had come to rely on steady funding. The logic for the change is clear. Advanced AI tools can speed experiments and lower the cost of drug discovery. Investing in that work could lead to new treatments faster than traditional grants. Acquiring talent and software gives the group in-house capabilities that many public labs do not have. The trade-offs are also clear. Money that once underwrote classrooms and community programs now backs lab-scale biology and proprietary platforms. That shift concentrates decision-making about what science to pursue inside a private entity. It also raises questions about accountability. Who decides which diseases get priority, and how open the resulting tools and data will be? This is not a simple right or wrong. The group can accelerate work that might save lives. It can also leave vulnerable communities with fewer resources. Which matters more to you, the speed of innovation or the protection of public services? Tell someone who follows philanthropy and leave your answer in the comments. There is a simple, practical question that follows the shift. Who sees the raw research first? Private labs can generate datasets and models quickly. They can also hold them behind internal walls for a time while they refine methods or seek partnerships. That can speed development. It can also delay independent checks. Partnerships with industry change incentives. When tools and data feed into companies that can commercialize outcomes, priorities shift toward projects with clear market paths. That approach can find drugs faster. It can also leave rare conditions and social programs with less attention. The balance between public good and private return becomes central. Regulators and universities now face new choices. Should funding from private groups require stronger open data rules when public health is at stake? Should grants that build shared infrastructure demand immediate public sharing? There are no easy answers, but examples from recent years show both models in action. Some projects published data openly and advanced work across many labs. Others kept early results tighter while they matured tools. The potential upside is real. AI-guided biology could cut years off the path to treatments. Faster discovery means lives saved. That is the hopeful side. The worry is about power concentration. When a small number of private actors set research agendas, the public may have less say in what gets prioritized. So here is the question to think about. Would you prefer faster breakthroughs led by private labs, even if that means less public oversight? Or would you rather slow the pace slightly while insisting on open rules and wider community benefit? Which matters more to you and why? Write your answer below and share this with someone who follows philanthropy. Richard Branson and Virgin Galactic. He built a company to take people to the edge of space and to open a fast lane for suborbital science. The firm moved from test flights to a new generation of vehicles called the Delta class, designed to fly more often and to carry more research payloads. That change meant investing in production, not just in prototypes. To support that scale, they opened a manufacturing facility in Mesa, Arizona. The space is for final assembly and for the higher cadence needed to aim for many flights each month. The idea is simple. If you can build more ships, you can fly more often and offer seats to tourists and lockers to researchers. Ticket pricing has been high. Seats are priced around $600,000. That number puts these flights in the luxury category, but it also funds sustained operations as the program ramps. The company projects that with steady scaling and 125 missions a year, the business could generate substantial revenue and move toward profitability. There is another business line that changes the math. Research payload lockers on suborbital flights can bring in $2 million to $20 million per flight, depending on how many experiments ride up. That range shows why universities and companies buy seats for short microgravity tests and atmospheric experiments. For them, a suborbital hop is a fast and cheaper way to collect data. So the pattern looks familiar. Private cash built a production line and a new vehicle class before the full market existed. When demand for tourism and fast research rose, there was commercial capacity ready. Is that visionary timing or an advantage that favors wealthy customers and private labs? Tell someone who follows space and leave your view in the comments. Scaling up brings new scrutiny. More flights mean more tests and more eyes on safety records. Regulators carefully review flight data and procedures. Communities near launch sites watch for noise and environmental effects. Proving a safe flight profile is as important as selling a seat. There is an environmental angle. Frequent suborbital launches increase fuel use and emissions. Companies argue that suborbital hops are a small fraction of global transport emissions. Critics say cumulative impact matters, and that regulators should account for local effects as cadence rises. The research market changes the value equation. Universities and small companies buy short microgravity windows to test hardware and biology quickly. Those research lockers can be worth millions per flight. That demand makes flights economically sensible beyond tourism alone. It also means scientific access can depend on institutional budgets or private partnerships. That creates fairness questions. Early access often goes to wealthy individuals and to labs with funding. Public research budgets vary by country and by institution. A private firm that can launch frequently will naturally host well-funded projects first. That ordering shapes what science gets done quickly and what waits. There is also reputational risk. High-profile failures or controversies can slow regulatory approvals and damage public trust. Successful frequent flights build market confidence and attract partnerships. The timing matters because capacity was built before demand fully existed. When demand arrives, private readiness becomes a powerful lever. So what do you think? Is early private investment in production and frequent flights a necessary engine for progress, or a way to give early advantage to wealthy customers and well-funded labs? Which matters more to you and why? Leave your answer in the comments and share this with someone who follows space. Larry Page and Google X. He funded a semi-secret lab that could afford to try risky projects. One of those bets became a self-driving car program that later spun out as Waymo. Over years, the project drove tens of millions of miles in tests. By 2025, Waymo reported autonomous driving experience across 13 states, and it offered hundreds of thousands of paid rides each week. Those numbers show what private time and money bought. Prototype work moved into real-world service long before many public programs could catch up. Another X project tried a different problem. Project Loon sent balloons into the stratosphere to carry internet where wires and towers could not reach. The system provided emergency connectivity after disasters in places like Puerto Rico and Peru. It proved the concept that high-altitude platforms can help when ground networks fail. The project faced commercial viability problems, and it ended in 2021, but it left behind engineering lessons and spurred other efforts. Here is the pattern. Private cash built experimental capacity for projects that later mattered to public safety and service. When disaster hit, or when autonomy became practical, there were teams and tested systems ready to scale or to inform public policy. That readiness is valuable. It can save time in crises and speed technology into everyday life. At the same time, private labs pick which problems to try. They answer some questions and leave others untested. When a small number of actors decides priorities who represents the public interest. Is early private experimentation the engine that benefits everyone or a concentration of advantage that needs stronger public oversight? Tell someone who follows tech and leave your thought in the comments. Private labs do more than build prototypes. They create teams, data sets, and tested systems that governments and companies can adopt. That creates speed. It also creates leverage. When a tested system exists, policymakers and emergency responders can rely on it quickly. That reliance shapes procurement choices and public policy. There are trade-offs. A spin-out that becomes a service can lock in design choices made under private control. Public agencies may prefer proven tech, even if alternatives exist. That reduces competition and narrows who sets standards. At the same time, proven systems can reduce risk and save lives when deployed in emergencies or in mass transport. Transparency is a recurring issue. Independent audits, shared datasets, and open testing protocols help build trust. Some private projects publish data and collaborate widely. Others keep early work proprietary while they polish products. The result is uneven accountability. Citizens and regulators must decide how much openness to demand when public safety is involved. There is a second lesson about failure. Project Loon ended because commercial paths were hard. That failure still taught engineers and regulators about high-altitude platforms and emergency connectivity. Failures pushed ideas into other hands. Private experimentation can seed public goods, even when the original project does not survive. So what should change? Stronger public-private agreements could require shared test data for systems that serve public safety. Procurement rules can favor openness and interoperability. Or we can accept private speed in exchange for less public control. Which side do you lean toward? Faster deployment with private leadership or slower progress with stricter public oversight? Tell someone who follows technology and leave your answer in the comments. Sergey Brin and the Google Lunar X Prize. The prize started in 2007 with a purse of $30 million to spark private teams to land on the moon and send back video. No team claimed the grand prize by the deadline. Still, the competition did something bigger than payout. It pushed private investment. Teams raised well over $420 million to develop landers, rovers, and descent systems. That money built hardware and talent in countries around the world. Teams experimented with tiny designs and new manufacturing methods. They used three-dimensional printing to make lightweight rover frames. They developed vision-guided landing sensors that can spot rocks and soft soil. Those sensors learned to read terrain and to help a lander set down safely. Compact communications and high-definition transmitters came out of the work as well. The competition also seeded companies that kept going after the prize ended. Some teams evolved into service providers and contractors. One former competitor went on to raise major funds and to sign commercial contracts. Another company that began in the prize era won a multi-year contract with a national space agency for lunar delivery services and continued development of precision landing tools. And then there are firsts that matter. In early 2024, a private lander reached the lunar surface and sent back data. That milestone shows the path from prize challenge to operational capability. The prize did not directly award that success. It created an ecosystem that made success more likely. So the key point is simple. A private incentive that did not pay out still changed the game. It drew capital, it pushed tech forward, and it helped private teams win public contracts later. Was that outcome a lucky coincidence, or precisely the effect the prize was meant to produce? Decide and tell someone who follows space. The prize left a visible trail that matters today. Private teams raised hundreds of millions of dollars to chase a $30 million purse. That level of investment built real companies and real skills. Some teams matured into providers that later won public contracts. One former competitor secured a contract worth $79.5 million from a national space agency. Another private lander reached the moon in early 2024 and sent back data. Those are not abstract wins. They are operational milestones that trace back to the competition era. The educational ripple was broad. The challenge inspired programs that reached hundreds of thousands of students. Young engineers learned to design lightweight rovers and to solve landing problems under tight budgets. That talent pipeline matters for the next decade of space startups. There is a policy lesson, too. Prizes can be catalytic. They focus energy and risk capital on a target, and they encourage international teams. They can produce public value even when the original prize purse is unclaimed. At the same time, prizes can favor teams that already have access to investors and expertise. That creates an uneven playing field. So here is the practical choice. Use prizes to spark innovation and accept that private capital will steer which problems get tried. Or fund more public programs that set priorities with stronger oversight and broader access. Both approaches have trade-offs. Which side do you take? Do private prizes produce public good fast enough to justify their unevenness? Or should public strategies insist on open access and wider inclusion before scaling capability? Tell someone who follows space and leave your view in the comments.